Hello everyone, my name is Tomoki Uchiyama. First of all, I would like to thank the competition organizers for hosting this exciting challenge. Today, I would like to talk about my solution. Here is the agenda for my presentation. I work as a R&D engineer at a manufacturing company, and my background is in computer vision. That's why I participated in this competition, which is an image recognition task. Now let's move on the main topic. And this is my pipeline to extract particle coordinates from tomograms. First, I obtain prediction maps of particle position using 10 unit models. Next, I binarize these maps and apply connected component analysis to extract particle coordinates. A key point of my solution is that I adapted a loss function suitable for this pipeline. Let's talk about the details. First, regarding the pre-processing phase. Normalization for each tomogram, I removed outliers based on percentile thresholds and apply min-max normalization. And I generated ground truth masks by creating spherical binary masks at annotated particle centers using half of the given particle radius. This is an example of ground truth mask. And the next section is about models. For models, I trained 10 unit models. I used both 2.5D and 3D models to take advantages of different architectures. This ensemble approach enhances the robustness and improves the detection performance. One important model is the 2.5D unit. And this is based on a public notebook. In this model, the 3D tomograms is encoded as a series of 2D slices. Then the 2D features are decoded with 3D convolution. For encoders, TIMS EfficientNet V2, EfficientNet V2 P2, ComNext Nano, and ResNet 34D were used. In addition, I used full 3D models. These models capture the 3D spatial context of the tomograms. I used Monai's 3D unit and SegResNet. Next section is about training methods. First, let's talk about the loss function. I found that dice and Tversky losses converge quickly, but don't tend to yield overconfident predictions. as shown in this figure. To fix this, I used the focal Tversky++ loss. This loss function imposes high penalties on overconfident and inaccurate predictions. This ensures better calculation, which is important for my pipeline and averaging prediction and thresholding. This prediction map is in the case using focal Tversky++ loss. And I also used data augmentation to boost the robustness with limited data. I applied random rotations, flips, blur, downscaling, Gaussian noise, brightness, contrast adjustment, and elastic transformations. And in addition, I pre-trained several models using simulated tomographs generated by Ornet. To enhance model discrimination, I included particles with shapes similar to competition's target particles in the simulation. This pre-training was particularly beneficial for the 3D architectures and 3D unit and SegresNet. Next, inference and post-processing. For inference, I use a sliding window approach with a 25% overlap and discarded the outer 8% of sub-volume predictions due to lower reliability. And I also use the TensorRT engine to make inference faster. And for post-processing, I binarize the prediction maps using class-specific thresholds. And then I apply connected component analysis on the binary maps. And finally, I extract particle coordinates by computing the centroids of the connected components. And the results. Here is the results. The left table shows the effect of ensemble. By ensembling, the scores have improved both in cross-validation and on the leaderboard. And the right table shows the effect of the focal Tversky++ loss. For example, using the 2.5D unit trained with models, I compared different loss function, and so that the focal Tversky++ loss improved performance. That's all my presentation. On my solution. Thank you for listening.